Hello students, I am Santanu Bhatia, currently studying MSc Physics in IIT ISM Dhanbad. Today I am going to teach you ampere circuital law. The definition of ampere circuital law is it relates the magnetic field inside a closed loop with the current passing through the loop. So the definition I am going to write is it So basically it relates the magnetic field passing the magnetic field with the current passing through it. Now it is basically a alternative process of calculating the magnetic field for a closed loop. Whether we have the Biot-Savart law, which is a formal process to calculate the magnetic field inside it. Now there is some special cases for which we can apply that law. The special case is, now we are taking a closed loop like this one, and if there is some current passing through it like this one and this one, we know that this represent a current which is in inward direction of the plane, that is in the inward direction, and this represent a outward direction current, outward direction. Then we can calculate the magnetic field at any point in the loop, for that current which is passing through that loop. Now considering a point P at the loop, now we have to calculate the magnetic field at point P. So considering the magnetic field at point P is B, and we know that whether the current is outward or inward, the magnetic field is always tangential to the loop, that is in that direction or in that direction. Now taking a small length element dl, that is dl, then ampere circuital law says that b dot dl close integration equals to mu 0 times I enclosed, where I enclosed is the total current inside that loop and mu 0 is a constant which is known as permeability. Now we are considering a special case where there is a circular loop we are considering, and that is the current which is passing inward outward direction, and the current value of the current is I0. Now we have to calculate the magnetic field at point P. Now we have to calculate first that B dot dl. Now we know that due to the current, the magnetic field at P is tangential to the circular loop. So angle between B and dl is 0 degree. So B dot dl is equal to B dl cos theta. As the value of theta is equal to 0, then cos theta equals to 1. So we will take B dl only. Then from we are numbering that equation as equation 1. So from equation 1 we can write that B dl close integration is equals to mu 0 times I0. Now as B is constant at any point in the circular loop, so we can take out that B part from the whole integration. So we can write that as B time close integration dl equals to mu 0 times I0. Now as dl represent a small part of the loop, so if we integrate the dl along the closed loop, we will get the total perimeter of that circular loop. So that will be B into 2 pi r, that is equals to mu 0 times I 0, where r is the radius of that circular loop. Then we can write that B equals to mu 0 times I 0 divided by 2 pi r. So that is the magnetic field due to a current passing outward direction, and it is a magnetic field at the point P. So as we have seen that this is a very easy process to calculate magnetic field due to any current carrying wire or any current carrying object. So we can calculate any magnetic field due to that very easily using the ampere circuital law. Besides that, we can also calculate the current magnetic field due to a cylindrical wire at any position of the wire, whether it is inside or it is outside. That's all for today. Now, for the second example, we are considering a cylindrical wire of radius r and a constant current density J inside that cylindrical wire. So, the constant current density given is J, and the radius of the cylindrical wire is as given, it is r. Now, we have to calculate the magnetic field at point P inside the cylindrical wire, where the distance of P from the axis of the wire is r. So this, as we have seen from the figure, is that r is smaller than r. R is smaller than r. So to calculate the magnetic field, we will use again the ampere circuital law, that is close integration B dot dl, that is equals to mu 0 times I enclosed. Now, the current enclosing that loop is basically the current inside that radius r. So it will be I equals to J time pi r square. Now we will use that in the equation 1. So by using it, we will get. Now from equation 1, we can write that close integration B dotted with dl is equals to mu 0 times, we will replace that I enclosed with the J times pi r square. J times pi r square. Now again B is constant around the closed loop, so we will take B out, then that will get B time close integration dl equals to mu 0 J pi r square. Now close integration dl equals to the perimeter of that loop, so we will get B into 2 pi r equals to mu 0 J pi r square. Then B equals to mu 0 J pi cancel out, and that square part will be cancel out, so we will get mu 0 J divided by 2 times r.